When someone asks me, why do magnets attract? Or what's going on between these two bits of metal when they push apart? Well, that's an excellent question. But the problem is, when you ask why something happens, how does a person answer why something happens? Let me give you an example. Your Aunt Minnie is in the hospital. Why? Because she went out, slipped on the ice, and broke her hip. Now, that satisfies most people. It's a perfectly good answer, but it wouldn't satisfy someone who came from another planet and who knew nothing about why, when you break your hip, you go to the hospital. How do you explain that? Well, you'd have to explain about pain, about medical care, about human physiology. And each of those explanations opens up more questions. You see what I'm getting at? The more you ask why, the deeper you go. And you have to decide at what level you're going to stop and say, that's just the way nature is. Now, if you're somebody who doesn't know anything at all about physics, all I can say is magnetic force makes magnets attract or repel, and you're feeling that force. That's one of the fundamental forces in nature. There are electrical forces, magnetic forces, gravitational forces, and others. Those are the basic elements of the world. That's one level of answer. But I can already see you're not satisfied with that. You want to know more. You want to know what's really happening. So let me go deeper. But I want to be honest with you. I can't explain magnetism in terms of anything else you're more familiar with, because I don't understand it in terms of anything else that you're more familiar with. I could say, for instance, that the magnets attract as if they were connected by rubber bands, but that would be cheating you, because they're not connected by rubber bands. And if you were curious enough, you'd ask me why rubber bands tend to pull back together again. And I would end up explaining that in terms of electrical forces, which are the very things that I'm trying to use the rubber bands to explain. So you see, I've gotten nowhere. I've just gone in a circle. This is the fundamental problem with explaining physics to someone who doesn't already have a framework of understanding. Every explanation requires some agreed-upon starting point, some things we just accept as the way nature behaves. But okay, let me tell you what we do know about magnets. Let's go to a deeper level. First, let's talk about what a magnet is. When you pick up two magnets and you hold them near each other, you feel something. Turn them one way and they push apart. Turn them another way and they slam together. What's happening? Inside every magnet, there are these tiny atomic magnets. Now, in most materials, in wood, in plastic, in your hand, the atoms are there. But their magnetic moments point in random directions. North, south, east, west, all jumbled up. They cancel each other out. No net magnetic field. But in iron, in nickel, in cobalt, in what we call ferromagnetic materials, something different happens. The atoms can line up. Billions and billions of atoms, all pointing their magnetic moments in the same direction. And when they do that, instead of canceling out, they add up. You get a big magnetic field from all these tiny atomic magnets working together. Now, you might ask, what makes these atoms magnetic in the first place? This is where it gets really interesting, and where quantum mechanics comes in, whether we like it or not. Inside every atom, you've got electrons. These electrons are moving around. They've got what we call orbital motion, circling the nucleus. And they've got something else, something very strange called spin. Now, don't picture a little ball spinning like the Earth. That's wrong, and it'll get you into trouble. The electron is, as far as we know, a point particle. It has no size. How can something with no size spin? It can't, not in the classical sense, but it has this property, this intrinsic angular momentum that behaves mathematically exactly like spin. And here's the crucial part. A moving electric charge creates a magnetic field. The electron has a charge, and its motion, both the orbital motion and this intrinsic spin, creates a magnetic field. Each electron is like a tiny magnet. In most atoms, the electrons pair up, one spinning one way, one spinning the other way. Their magnetic fields cancel out. But in iron, in cobalt, in nickel, you've got unpaired electrons, electrons whose magnetic fields don't cancel. And more than that, and this is the really special part, in these materials, the electrons in neighboring atoms like to point in the same direction. They cooperate. Why do they cooperate? Well, now we're really getting down to quantum mechanics. There's something called the exchange interaction. The Pauli exclusion principle says two electrons can't be in exactly the same quantum state. When electrons are close together in a solid, this creates forces between them, not the ordinary electrical repulsion you might expect, but something more subtle. These quantum mechanical forces favor having the electron spins aligned in the same direction. And so you get these regions, we call them domains, where millions of atoms all have their electrons pointing the same way. In an ordinary piece of iron, you might have many domains pointing in different directions, still canceling out overall. But if you put that iron in a magnetic field, the domains that are already pointing along the field direction grow bigger. The boundaries between domains move. More and more atoms get lined up. And if the field is strong enough, nearly all the domains point the same way. Now you've got a magnet. You're holding this piece of iron, and inside it, billions upon billions of tiny atomic magnets are all lined up, all pointing the same direction, all adding their little contributions together to make one big magnetic field that you can feel. Now, when you bring two magnets together, their magnetic fields interact. If you point the north pole of one magnet toward the north pole of another, the fields push against each other. The field lines are trying to go the same direction out of both magnets, and they can't occupy the same space. They repel. But if you turn one around and bring a north pole near a south pole, the field lines want to flow from one to the other, from the north pole of one magnet into the south pole of the other. The fields complete each other. They attract. You might ask, what is this magnetic field really? What's actually there in the space between the magnets? And now we're at another level of why. According to classical physics, the magnetic field is just a mathematical description. It's a way of saying if I put another magnet here, it will feel a force in such and such direction. The field is just our way of describing how one magnet affects the space around it such that another magnet will respond. But in quantum mechanics, we have a different picture. We say that magnets interact by exchanging virtual photons. These are photons that pop in and out of existence so quickly that you can never catch them. They're allowed to exist temporarily by the uncertainty principle. One magnet emits a virtual photon, the other absorbs it, and that exchange creates the force between them. Now, is that the real explanation? Well, it's the best explanation we have at the quantum level. It makes predictions that match experiments to an incredible degree of precision. But you might ask, why do virtual photons exist? Why does the uncertainty principle work that way? And now we're back to the same problem. We've just moved the question one level deeper. You see, at some point we have to say, this is how nature works. This is what we observe. We've described it mathematically. We can predict what will happen, but we can't explain it in terms of something more familiar because there isn't anything more fundamental to explain it with. We've hit bedrock. Let me tell you something that might surprise you. The electrical force, the force that keeps your hand from going through the table when you put it down, the force between a proton and an electron, that's the same kind of force as magnetism. They're not two separate things. They're two aspects of the same underlying phenomenon, the electromagnetic force. In fact, whether something looks like an electric force or a magnetic force depends on your frame of reference. If you're moving along with a charged particle, you see one thing. If you're standing still while it moves past you, you see something different. What looks purely electric to one observer looks like a combination of electric and magnetic to another. Einstein figured this out, and it led him to the theory of special relativity. So magnetism, electricity, they're deeply connected. Maxwell in the 1860s wrote down 4 equations that completely describe how electric and magnetic fields behave. Those equations are some of the most beautiful in all of physics. They tell you how moving charges create magnetic fields, how changing magnetic fields create electric fields, how the fields propagate as electromagnetic waves. Light itself is just electromagnetic waves. And yet, for all this mathematical beauty, for all our equations and quantum mechanics, I still can't tell you why in the deepest sense. Why is there an electromagnetic force at all? Why do electrons have the charge they have, the spin they have, the magnetic moment they have? We measure these things, we describe them, we make predictions with them. But why nature chose those particular values? Why the laws are what they are? Those questions we can't answer. Let me give you another example of how deep this gets. You might have heard that the strength of the electron's magnetic moment has been measured to incredible precision. The theory says it should be 1.01159652218 times a certain basic unit. And the experiments confirm this to 11 decimal places. It's one of the most precisely verified predictions in all of science. But why that number? Why not exactly 1.0 or some other value? The answer comes from quantum field theory. from the fact that the electron is constantly emitting and absorbing virtual photons, from the structure of the vacuum itself. We can calculate it, but we can't say why nature works that way rather than some other way. You know what's really remarkable? For all these deep questions we can't answer, magnetism works. We use it every day. Electric motors, generators, hard drives, MRI machines, speakers, microphones, all based on electromagnetism. We can design these things, build them, make them work without knowing the ultimate why. It's like being given the rules of chess without being told why those are the rules. You can still play the game. You can become a master. You can appreciate the beauty and complexity. You just can't say why the bishop moves diagonally rather than in straight lines. That's just how the game is played. Physics is like that. We've discovered the rules nature plays by. We can use those rules to make predictions, to build technology, to understand the universe, but the ultimate why these rules and not others, that may be unanswerable. Or maybe we'll find a deeper layer someday. Maybe there's a more fundamental theory that explains why the electromagnetic force has the properties it does. People are looking. That's what string theory and other approaches are trying to do. But here's what I want you to take away from this. When someone asks, how do magnets work? They might want any of several different answers. They might want to know about domains and aligned atoms. That's one level. They might want to know about electrons and quantum mechanics. That's deeper. They might want to know about virtual photons and quantum field theory. Deeper still. And at each level, the answer is satisfying if you're willing to accept the starting assumptions of that level. But if you keep asking why, you eventually hit the foundation where all we can say is, this is what nature does. And that's not a failure of physics. That's the nature of explanation itself. The amazing thing, the really astounding thing, is that we can go as deep as we have, that we can describe the behavior of magnets using the same theory that describes light and radio waves and X-rays, that we can make predictions accurate to 11 decimal places, that we can understand the connection between electricity and magnetism and relativity, that we can trace it all back to properties of electrons and the fundamental structure of quantum mechanics. That's pretty good for a species of apes that only started doing science seriously a few hundred years ago. So, when you pick up two magnets and feel them push apart or pull together, you're feeling the combined effect of billions of atomic magnets, all aligned together, creating a field, exchanging virtual photons, following the laws of quantum mechanics and relativity, all acting together to create that push or pull you feel in your hand. And somewhere at the bottom of it all is the simple fact that electrons have charge and spin and create magnetic fields. And we don't know why they do that, except that they do. And that's what makes the universe interesting. That's magnets. And if your brain hurts a little, well, that's perfectly appropriate. Mine does too. And I've been thinking about this stuff for 50 years.